it's a thin water shaft, right? Thin water shaft under under torque. So we want to know the maximum possible. No. We want to know the rate of twist, dz, assuming and also shear flow. Well, if you don't have shear flow, you cannot find this one. For thin water shaft, everybody knows that shear flow Q is equal to what? T0 over 2A, right? And the shear stress divided by thickness. Well, our problem is to relate this one and the angle of twist along the length. Well, to do this, actually we can have two ways, right? I prefer to use the energy method because, see, for this kind of thin water shaft, it might not have a regular cross section. It might have cross section like this. So the shear strain everywhere shear strain is not uniform. And if you use traditional method, I think it's a little bit cumbersome. So I prefer to use the energy method. How to apply the energy method? Assuming we have a cross section like this. So first we need to know, assuming the length is L, we want to know how much strain energy is there for this section under torsion. So in torsion case, the strain energy tau gamma, and gamma is also, because gamma equal to tau divided by g, so tau square. This is the U, and for unit volume, and for this whole volume, dV U times, what is dV? dV is L times the thickness and times the arc length, the length of the curve, ds, right? This is ds, and we want to know the whole, the area of this region. Then ds, we take the integral over the whole region, and also times the thickness, t. Oh, you don't know how to write strain energy. Do you know what the strain energy is? No, you don't know. Okay. Okay, then. Then we can go with traditional method. for this case, if we take a small section, to consider we're gonna use the force analysis to find how to relate the angle of twist, this twistor rate to the torque. So if we take this small section out, and assuming it has the shear deformation, right? So eventually, the gamma will be phi 1. Well, this is for small deformation, right? Phi 1 plus phi 2. Phi 1 plus phi 2. And you can also, so the shear flow is times thickness and times gamma. And what is phi 1? So phi 1 actually, for small deformation, phi 1 equal to approximately equal to tangent phi 1. So which is defined by this displacement. This is along, we can say this along the curve. So we use US represents its displacement. So equal to US divided by what? This is in z direction, right? dz. And by the same token, we can find phi 2, tangent phi 2, right? This is also approximately equal to tangent phi 2. This is displacement in z direction, duz, and divided by this distance, ds. And okay, to find a total displacement, right? Here, Q. From this equation, we have okay. Let me go here. From this equation, we have gamma equal to Q divided by GT. And we want to know, because gamma here is a deformation, right? We want to know how much rotation we have at the end. So we should have a we should integrate this through all this parameter. And it should equal to, well, this one, right? Can you understand this step?
Yes.
Okay. If you don't have a problem in understanding this step, then we can go for we can proceed. See, ds here, nothing. So you actually you want to know the total displacement in z direction. But in torsion case, we assume there's no axial displacement, which means this whole term reduces to 0. And this is the only term left. Well, What is du? Du is, we can see du is, assuming this is a distance, right? D rho. And this is, well, I want to use another section. This is d rho, and this is du, dus. It's the displacement along this perimeter, and this is the distance from the centroid of this cross section to the line, the action line of this displacement. So and d phi. To find du, dus is times right. So here we can have d phi over dz, assuming it's a constant, because for thin water shaft it's always a constant, right? We get everything out. And a q also is a constant. Rho ds. And what is this? This is 2a. Because, see, d rho times ds, dus. I'm sorry, this is ds. This arc length. This arc length, and this is equal to 2 times of the area of this triangle. So, if you integrate over ds, over the whole surface, then I'm sorry, not surface, over the whole curve, you will eventually have 2a over here. So and gt, g is constant here, and t, wall thickness, well, assuming it's constant too. Get everything out, and you are doing integration for this curve segment, ds, and you will have eventually you will have s. So q, 2a, and g, t times s. This is the rate of twist. You know the geometry. You know how to find the length of S, and you also know how to find the area of A. So this is the expression for the twist rate. Okay, any questions? And then let's proceed to the third problem. The third problem, I think, the third and the fourth are relatively easier than the first and the second. And the width, assuming this is a rectangle cross section, okay? So the width is b. The same for this one and this one. So we're given the strength. So we want to know what's the maximum possible P. This is similar to the first problem. To find the maximum possible P, we first need to find the location and the value of the maximum longitudinal stress under bending. So you can imagine it must occur for each section. It must occur at the outermost part, right? But we don't know, since it's not the cross section is not uniform. We don't know where this maximum value. We don't know where it either occur here or occur somewhere here. Okay, then we start from basic, from very beginning. So, assuming we have V and M here, we call it VR. I'm not sorry, not V. FR, Y. Okay, this is X direction, and this is Y direction, and this is Z direction. So MZ, MRZ, okay. R represents reaction. So FR, Y equal to P, and MRZ equal to, sorry, wait a minute. No, I'm not going to use. I tend to use this direction. So we have a positive sign. So if you use this, MRZ equal to PL. 2PL. And for each section in the middle, we can find the based on the equilibrium of moment M X. Assuming here the bending moment is M, also in this direction, so it's positive, right? Plus MR Z minus. Why minus? Because F is pointing upward. So the moment generated by F at this distance, X, should be minus FRY times X. Is equal to 0. And you can find am I right? So for bending, to have bending maximum possible bending, to have bending stress generated by bending, usually we can I and times Y. This is a formula for sigma X. But we have different I. Well, we have different IZZ here and different IZZ here. So for this section, IZZ equal to 12 B 2H. And this is when X and also IZZ when X is from L to 2L. So we can see from the expression for M, it goes linearly from this point to this point. So for each section, the maximum bending moment occur here for this section occur at the root, and for this section it will occur at this point, right? And what we need to know is to find sigma x for both two locations. So for this location, say let's say this is A and this is B. This m equals to 0, so minus 2pl divided by what? And times h. And for this section, for the later section, here is I would say and another so what's this value? And this one is we can find the stress at this point is 2 times as much as the stress at this point. So here actually is the maximum stress point for the whole beam. Then only when this is less than or equal to sigma y, this beam will not fail, right? And so, well, you can put it back and find what the P is. Any questions regarding the explanation? Do you have any questions on all the procedures? I think it's quite straightforward, right? Everyone, I hope, have no problem with that. And the last problem, last question, I think it's the simplest one. What you need, I think the thing you need to pay attention to is that, see this moment, oh, so no. This moment passes through the centroid of this cross section, this bending moment. Well, moment is also vector, right? You don't need to calculate the moment of inertia with respect to this axis, because in this case you need to have a complex formula. You need to consider a lot of rotations like sine, cosine, which is not necessary. Moment is also a vector, so you can decompose it along two principal axes. Well, usually, see, this is a cross section, right? And we usually, if we rotate this cross section by 45 degrees, I mean, whole diagram by 45 degrees, and counterclockwise, then this will be y, and this will be z direction, while this is x, right? Usually we have x along the axial direction, and y is vertical, and z is perpendicular to the surface. And the moment will be like this. It's m0. So if we decompose this m0 along both y and z direction, this is also vector, okay? And so we will have a moment. We will have a moment my. Oh, sorry, this is mz. mz equal to minus and also we have a my equal to this negative sign is because of the direction of this moment is opposite to the right direction, to the positive direction of the z-axis. That's why it's negative. And just imagine under this kind of bending moment, say if we only consider the bending moment along z direction, and we will find that the upper surface is under tension while the lower surface is under compression, and this is where the maximum stress is, right? And if you consider this y, the bending moment along y-axis only, you will find you will have the tension side here and compression side here. So just imagine tension and tension. Here should have the maximum possible. Here should have the maximum tensile stress under this combined torsion case, combined bending case. And another thing I want to mention here is that when you calculate the bending stress, do not simply use the formula sigma x equal to minus m divided by I times y or something. This is only valid for this y direction. While for z direction, you can imagine if you apply, if you apply a say bending moment along along y direction, right? Along y direction, and it's positive. So the tension side should have the positive coordinate, while the compression side should have a negative coordinate. It's different from the usual case. In usual case, we apply z, right? We apply torque. I'm sorry, bending moment along z direction. So under the positive y side, we have compression, and the negative y side, we have tension. It's just reversed. So in this case, if you want to calculate the total stress at each point, at any point within this cross section, this is mz plus, this is plus my Iyy times d. So Izz, this is h, and this is 3h. So Izz is the moment of inertia about the z direction, right? About the axis. So B here is h, and the height is 3h. And I, in this case, if you calculate the moment of inertia about the y-axis, here B becomes 3h, while h is just h. So put it inside, and see, we can sigma x max should be IZZ is 4 9h to the 4th power, and mz, what is mz? Okay, m is minus m naught divided by, since it is a 45 degree, right? 45 degree. And times what? If you, this is times 1.5. No, sorry. 1.3, 1.5 h plus this is what? Okay, and eventually you will get somewhere, let me see. Right? This is the final result. And that's all the solutions for the quiz. Do you have any specific questions regarding any problem that I have covered? Well, one student asked that why mz is negative. See, this is the definition of positive direction. Y is like this, and z is like this, and the moment, the bending moment is applied in this direction. This vector, you decompose it, you will have one component along y positive y direction and one component along negative z direction. That's why it's negative. Or is there anything that you need me to explain in more detail? Well, if everything's okay, then I assume that's the end for this class.